Alright, so if you're watching this video, you're about to watch me lecture on section P1. And because this is kind of the first section we do in a semester normally, I just wanted to talk a little bit about how you can be successful in my class, what you should do, what you might want to do while you're watching the videos to be as successful as you can in this class. And maybe some tips about avoiding computer outages, because sometimes our campus computer network is down, and which makes my material harder to access if you don't think ahead. So first of all, just for the heck of it, might as well introduce myself. My name is John Grima, and I started teaching at GCC Maine in 1994, and I transferred up to GCC North in 2001, and I've been here since, so I'm getting to be an old-timer, I guess. I don't have a doctorate, so you can definitely just call me John if you care to. That's completely fine. That's kind of what most people wind up calling me. If you really feel the need, you can call me Mr. Grima. When I first started at GCC, because I was young, nobody really called me Mr., but now it's fairly common. I'm more or less used to it, so you can definitely call me that. But you probably shouldn't call me Dr. Grima. I just have a master's and not a doctorate, and so calling me doctor is giving me a little more credit than I actually deserve. For what it's worth, I did my high school at Thunderbird, and while I was at Thunderbird, I also went to GCC Maine, because North didn't exist back then, and then I went to NAU for my bachelor's and my master's. I have a bachelor's in accountancy and a master's in math. Not that that really makes any difference, but that's just a smidge about me. So my whole course either operates from my webpage and or my YouTube page. My webpage address is on my syllabus, and so you could just go to my syllabus. Well, if you happen to have, if you came to class and you have my syllabus, you can go to my syllabus, type in the webpage address, and that should take you right to my webpage. I'm not terribly good about typing webpage addresses, so I don't ever use that. Another way to find me is just go to YouTube. And then search my name. And that will take you to where this video is stored. And it'll take you to my YouTube page. And on my YouTube page, there's a link to my web page, and so that's what I'm going to do now. I already searched on YouTube. I'll show you that you can just click and find my web page from YouTube, and my web page is way more organized than my YouTube page, so more often than not you're going to want to use it to navigate through my material. So I just did a YouTube search for me, and I come up top, number one, John Grima, I guess. And so if I just click on me, that gets you to my YouTube page, and right on the top of it, in the upper kind of right hand corner, you see a link that says my web page. That's how I generally get to my web page if I'm on a computer that I haven't already bookmarked my web page. Once you get to my web page, there's announcements on the front page, and there's a link for intermediate algebra. You should always read the announcements for your class on the front page. Right now, if you're taking intermediate algebra, and it's probably math 122 or math 120, it basically, and we're on summer vacation, so it just says enjoy your summer. But it does mention that for my class, I really like you to have a specific calculator. And so you're going to want to, before you get too deep into the class, get this calculator. It's not, you can't see it. You're going to want to get this calculator if you can, and it's under $20. So I've seen it for $12, like in like August before school starts. It's like sometimes on a special. Online, I've seen it for kind of $12 or $13. I know I'm not promoting Walmart, but they sell this at Walmart, Office Max. For whatever reason, it's not at Target. But you can definitely find this calculator, and even if you already have a calculator, it will likely be inferior to this calculator for our class, because this calculator just does some amazing things that even my Texas Instrument graphing calculators don't do. I have a TI-83 graphing calculator, and for most everything other than graphing, this calculator is way easier to use, and it does more than that. And regular price is about $18. So you should definitely, before you get too deep into the semester, get this calculator. And you don't have to be able to do anything on this calculator, anything that's more than adding, subtracting, multiplying, and dividing that this calculator does. I will show you in the video which buttons to press and how to get the output that you want to get. And you're allowed to use this calculator on the test. We can use a graphing calculator on the test too, but this calculator is definitely going to be the one that you want to have. So, make sure to go out and get that. So, in addition to the announcements, which we'll always mention about when our next test is and anything that might be due, there's a link to everything I have for intermediate algebra, and that's on the intermediate algebra page, and it's reasonably easy to find, so I'm going to go navigate to that real quickly. So my main web page, the front page, you're really only going to look at announcements there, and there's some other links like for GCC find a class and just some other generic links, but basically you're going to use my web page for announcements, and then the front page for announcements. And then you'll just navigate to the intermediate algebra links. So if I follow the intermediate algebra links, it takes me to all the material I've written for my intermediate algebra class. There's no book to buy for this course. Everything that you need for this course is on this web page. And if the bookstore sold you a book, you might as well take that thing back. More or less, I've recorded videos to kind of, replace coming to class for the most part for my hybrid classes, and videos for my in-person classes for students to watch if they didn't understand what I did in class or if they missed class to watch. So since we're going to do section P1, I'll talk about how I might, go through P1 to get the most out of it that you can. So first of all, I'm probably going to want to open a few documents. I probably want to open the chapter P. Sorry, I was writing without letting you see what I was writing. So there's no book to purchase for this course. I'm lecturing on P1, so I'll talk about how to go through P1, how I would go through P1 if I was doing that. So from my web page, you're going to want to open the chapter P problems at a minimum, and the chapter P answers. And it's optional, but not a horrible idea, to open up the chapter P solutions. And I'm not sure if that's one document or if I have a separate document for each section in chapter P. So I'll click on the links to figure out which one of these makes sense. So this is kind of my book, since we don't have a book to purchase. And in my video, when we finally get to start doing the video for chapter P, on my video of section P1, I'll talk about the concepts in the section, and I will also solve every even numbered problem. So I'll do 2, 4, 6, 8 all the way to the end of the section. So mostly my videos are me doing even number problems, which you'll find on the Chapter P problem. So let me open that up just so you can get an idea of what my problems look like, and I'll try to connect that to my video and what you should be doing while you're watching my video. So if I click on the link, there's Chapter P, if I click on the link that says Problems, the first thing that comes up is the section P1 Problems. If you scroll down, this link will contain the problems for every section in Chapter P. I think there's 7 sections. But for now, I'll focus on section P1. When I finally start doing my lecture over section P1, pretty early in the lecture, I'm going to start doing every even number problem. So at some point, I will likely, the first problem I will do is problem 2. And the idea is I always pair even and odd problems. I do an even problem, and the best thing you could do while watching the video is watch me do an even number problem and then pause the video and then do the problem that's directly preceding it. So when I get to doing the problems, when I do section P1 problem 2, watch me do problem 2. Hopefully I lecture well enough that you understand P2. Pause the video and then you yourself try section P1 number 1. If you feel comfortable, you might try section P1 number 3, section P1 number 5, section P1 number 7. You might be able to, while you're just by watching one problem in a grouping of problems, do every problem in a group of problems, which would be nice, but you may not be able to. At a minimum, after watching me do P1 number 2, you should be able to do P1 number 1. And after you do section P1 number 1, you should check to see if your answer is okay, because doing a problem, I make a lot of mistakes, so it doesn't guarantee you that your answer is right. So after I do a problem, you should do a problem. After that, you should check your answers. And to find the answer to problem P1 number 1, I should click on my answer link for Chapter P. So I'm going to do that real quickly to show you. After you do section P1 number 1, if you click on the link that says answers, then you'll see the answer. So if you did P1 number 1, you can see your answer should be that. If your answer is not that, then maybe go back and watch the video. Maybe you just misinterpreted something I said, or maybe you just didn't understand well enough the concept. And if you can't, by watching my video, figure out how to do an odd problem because you can't get your answer to match, that's the time where I'd go to the optional, opening the solutions. In the solutions tab, I have worked out every problem the best I can. Some of the problems I show a lot of detail if they have a lot of algebra to do. Other problems, the solutions aren't so detailed. So if you did section P1 number 1 and you didn't get the right answer because you checked your answer and it was wrong, then you'd go to my webpage, go to Chapter P Solutions. Yeah, now the solutions are separate for each section because some of them are kind of long. So if I click on the section P1 Solutions, if it's a problem that has any significant algebra, I will explain here how I got my answer. So the solutions, you may never open those because if you get the answer right for a problem, you're not going to look at the solutions. If you get the answer wrong, you might watch my video again, and that might inspire you to get a correct answer. But if my video doesn't inspire you, then clicking on the solutions, then maybe that will help you figure out the answer. So for this section, a lot of the problems don't have a lot of algebra, but any algebra that there is necessary for a problem will be contained on the solutions link. All right. So again, just to review, you should, while you're watching the video, when I do an even problem, you should immediately pause the video and try to do any odd problem that's in the same grouping with that problem, and do as many as you can. If you can do like the first group of problems, they're in section P2. I don't know how many problems there were. There were about 14 problems. Maybe with me doing section P1 problem 2, you're able to do all the way through 14. do all, which means every odd problem, 1, 3, 5, 7, 9, 11, and 13. If by me doing number 2, you're able to go and do all the problems between 1 and 14, the odd problems, you check your answer and they're all right, then you're probably going to fast forward my video and not watch me do every single problem between 1 and 14. I will do 2, 4, 6, 8, 10, 12, and 14, and you may need to watch me to do every one of those. You might need me to do, you watch my explanation for number 2 might inspire you to do 1, my explanation for number 4 might inspire you to do 3, but you'll kind of gauge yourself how much of my videos you do or don't need to watch. My videos get kind of long. Some students wind up having to watch me, they'll watch me do a problem in section P1 and they'll rewind it and they'll watch it again, they'll rewind it and watch it again until they understand it. Some students, they'll watch one problem in a grouping and that's enough. They won't watch me do all 7 problems in a group of problems. And that's completely up to you. But while you're watching my video, it should be really interactive. You should definitely be doing at least the odd problems and possibly even the even problems. So the first thing I'm going to do is, section P1 number 2, and then the next thing in my video, I'm going to do section P1 number 4. It would be nice if before I did number 4, you tried number 4. If you feel like you understand how to do a problem before I do it, then you should try it. You should pause the video. If you think you can. The more you're doing, without watching me do the problem or before I do a problem, the more you'll probably get out of it. Because it's easier to watch me do a problem and think you understand how to do a problem than it is actually to do a problem. So try to make these videos as interactive as you can, and I do every even problem. I ask you to do every odd problem in every section, and there's a bonus for that, and I'll talk about that in a second. You should be pausing my videos, doing the odd problems while you're watching the videos. You should be pausing my videos and trying to do an even problem before I do an even problem. And if you do all of that, then you should do really well in my class. I never ever ask a test question that isn't like one of the homework questions. So if you've done every homework question, you should be really prepared for it, any test that I give. And lost my train of thought. Oh, homework. And by doing the homework, not only will it make you understand the material better, it will give you a bonus. And before every test, I will post an announcement on my webpage, and I'll say something like this. I'll say, turn in chapter P homework by, and then I'll give a time and a date, and I'll say, and if you do this, you may use a 3-inch by 5-inch note card when you take the test. So not only does doing all the odd problems, by the homework I mean every odd problem in every section for a chapter, if you give that to me by the deadline that's written on my webpage, on the front page of my webpage, then when you go to take the test, you're allowed to use a 3-inch by 5-inch note card in addition to your calculator. If you don't do the homework, or if you do the homework and don't turn it in by the deadline, then when you take the test over a specific chapter, you're not allowed to use a note card. A lot of my students, because it's a hybrid class, they're not on GCC North's campus that often, and most of my students, instead of bringing their homework to my office, they either scan their homework or take pictures of their homework, and they just send it to me via email. So you can, for turning in your homework, You can definitely turn your homework in person. That's probably the nicest way. Or you can scan and email, which is also nice. Or you could take a picture and email. Sometimes, you know, you get so many pages that this taking pictures and emailing it gets to be a nuisance. But a lot of students still do that. The picture and email, you know, if you have any sort of smartphone, it's kind of easy to do. So it's a huge bonus. Generally, students that use a note card on their tests do a lot better on my tests than students that don't use a note card. Probably because they've done the homework as much as anything. The note card is a nice thing to have there. A lot of times when students, you know, get the luxury of using a note card, they don't wind up even using it because they know the material so well, and my tests aren't designed to be that hard that they don't even use it and they still get A's. Oh, that's already a lot, and I know this section is getting kind of beefy. So maybe I'll start lecturing right now. Just maybe one quick thing. You know, by the time you watch every video in a chapter, you should know all the material well, probably well enough to take a test. But always, for me, the last section in every chapter is called a review section. And the review section is guaranteed to be a lot like the test. So that there may be a lot of problems in chapter P that don't have problems that look similar to them in the review section. This is because I won't have you study every single problem in every single section of a chapter before we take a test. When we get to the last section, I take the most important problems and make up new problems, and I call it a review. If you could do every problem in the review section for a chapter, then you can do every problem on the test. I will never put a problem on a test that isn't real similar to something on the review. So by doing the homework in the beginning sections of the problem, that should give you the ability to do every problem in the review and problems that aren't on the review. But if you can do every problem in the review, then you should be able to do every problem on the test, because when I write my tests, I have the review open and I only ask test questions that are worded exactly like the review questions. Okay, that's gotta be enough. So now I'm going to lecture on section P1. Some of my lectures are, I think, better than others. Some are not better than others. Some things are just easier for me to explain. Some are harder to explain. Some of the stuff at the very beginning of the course, for me, is the hardest to explain because it's just definitions and not a lot of algebra. Section P1 would definitely fit that mold for me. The problems in P1 aren't super hard, but there's a lot of definitions and terminology that we need to learn. And on tests, I don't ask definitions and terminology. So the kinds of problems that I'm going to do maybe in the first 14 problems, there'll be words that I use in the class, but probably not something that creeps onto the test. If when you watch a video this semester, if there's a video that is just really awful, then you should just tell me. And if I get 2 or 3 students saying, hey, this video of section 1.4 was just ridiculously horrible, then I will re-record the video. Also, when you're watching the videos, I do make mistakes. So if you see me do something and you know it's wrong or you think it's wrong, then let me know. Because again, if I wind up having like 3 mistakes in a video, usually I just re-record the whole video. So there's definitely going to be times this semester where you're watching a video and you're like, no, and that's wrong, that's wrong, that's wrong. Sometimes I catch my mistake a little bit after I make it, but sometimes I never catch it. And if there's a mistake, then I want to let everybody know, because maybe you found my mistake and somebody else didn't, so I can write a little note so that everybody knows, hey, he was an idiot when he did that problem, so I can not teach you wrong things. Okay, now it's section P1. So in section P1, the first problems just are terminology problems, and for each problems between 1 and 14, I'm asked to identify, and so identify kind of clues me into there's no algebra. And the three things I'm asked to identify is a base, an exponent, and a coefficient. And I'll use these words, base, exponent, and coefficient, frequently when I lecture on chapter P, so they're good words to know. The easiest thing to identify, and that's never going to be tricky, is the exponent, and that's kind of, it's going to be raised. And in this problem, the 4 is raised. And what an exponent generally tells me to do is, an exponent usually means it's a shorthand for repeated multiplication. So I'll just say an exponent, at least when it's a positive integer, is a shorthand for repeated multiplication. So an exponent of 4 tells me I want to multiply something by itself 4 times. And specifically, the exponent tells me to multiply the base by itself 4 times. The base is generally the number or letter that's directly connected to the exponent. So the base could be a number, it could be a letter, and for letter, I'll sometimes use the word variable because that's the correct algebraic name for a letter. Letters are called variables because their value varies from problem to problem. I don't know what the y stands for here. In one problem, y might be 6, and another problem, y might be 2/3. So the base is the number or the letter that the exponent applies to. And it's usually just a single number or a single letter unless there's a parentheses. Unless the exponent is outside of parentheses. So let me read that again in case you can't read my writing. So it says the base is the number or letter, parentheses variable, that the exponent applies to. It is usually a single number or letter unless the exponent is outside of parentheses. So in this particular problem, the letter that the exponent is attached to, just the y is considered the base. The 7 is not considered part of the base and not considered part of the repeated multiplication because it's not in a parentheses. So had this problem said 7y to the 4th, the exponent, I'll just write exp, would be 4, and the base then would be 7y. So if there isn't a parentheses, then the base is just the letter or number that's directly attached to the exponent. When there is a parentheses, then the base is the entire contents of the parentheses. So no parentheses, the base is just the number or letter that the exponent is completely attached to. If there is a parentheses with an exponent outside of it, then the base is the entire contents of the parentheses. The last part of this is the coefficient, and usually I write that C-O-E-F-F, and I'd say the coefficient is the number in front of the letters, I suppose, might be fine to say. The number in front of the letters when there's no parentheses. Out of room, it's the number in front of the parentheses if there is a parentheses. So for the coefficient, it's generally the number in front of the letter when there is no parentheses. So in problem 2, so you already saw my first mistake. Hopefully you caught that. And a lot of times this happens. I make a mistake and I catch it. And this is I just caught it. So hopefully you're ready to send me an email telling me I made a mistake. Because in problem 2, the base was not the 7. The base was the y, because the y is what the exponent applies to. The number in front of the letter when there is no parentheses is called the coefficient. So that's going to happen, more than I care for it to happen. Sorry about that. But more often than not, when I make a mistake, I catch it like that. So that's, it's a bad thing, but hopefully when you see me make a mistake, you know it. And that's the best thing, because if you see me make a mistake and you know it's wrong, then you really understand something, and that's actually, not a bad thing. And this problem up here, which isn't one of the homework problems, but I was just trying to illustrate the difference between parenthesis problems and non-parentheses problems. In the coefficient in a parentheses problem, when there's an exponent outside the parentheses, room again, it's the number outside in front of the parentheses. So is the number outside the parentheses? I don't see one here. So in this little version up here that looks like problem 2, that's not problem 2. In that problem, the coefficient is the number outside the parentheses, and hopefully you know that if no number is written outside of parentheses, there's an implied 1, and in this problem the coefficient is 1. That's everything I did need to do for problem 2. This is just to illustrate how problems can be different when we have parentheses. And any problem that has a integer exponent could be written without the exponent. And again, this is a little extra just to help you understand the difference between 7y to the 4th without a parentheses and 7y to the 4th with a parentheses. So every exponent, if it's an integer, it's a shorthand for repeated multiplication. And an exponent tells me to multiply the base that many times. So this problem where 7 is the coefficient, y is the base, and 4 is the exponent, the shorthand y to the 4th, which is the base with the exponent, can be replaced with that. So 7y to the 4th means there's 1 7s and 4 y's, because the base is only the y. The y gets, if I'm writing the problem without the exponent, there's 4 y's to get rid of the exponent. Whereas in problem, that's not numbered, but in this problem, to write this without the exponent, I'm going to probably need some time signs. These little dots are time signs. This means 4 7y's being multiplied by itself, because the base is 7y, and an exponent tells me to multiply the base by itself, in this case 4 times. So this version, I multiply the y by itself 4 times if I want to get it into a non-shorthand version. This version, I get 7y by itself 4 times. That's probably way overkill for these problems, but I just wanted to get everything that was in my mind out, and now I'm going to go through the next problems a little bit faster. So and again, you should probably pause the video now. Try to do as many of the problems between 1 through 14, 1, 3, 5, 7, 9, 11, and 13 that you can. Every time you do a problem, you should check to see whether your answer is right or wrong by looking at the answers. And if you get a wrong answer, then watch more of the video or read the solutions. So there's no algebra to do for any of the problems between 1 and 14. And for each one of these problems, the exponent's not going to be the tricky part. And if I'm doing problem 2, well, if I'm doing problem 4, I always, the exponent, I get it first because it's the raised part. So in this case, the exponent is 2. Since there isn't a parentheses, then the base is just going to be the number or letter that's directly next to the parentheses, which is going to be the letter Z. And when I write my Z's, I write a line through my Z, otherwise they start to look like my 2's sometime. So you always see my Z's with a line through them. And then because there's not a parentheses, the coefficient is a number in front of the letter. And I'm going to abbreviate that again as coefficient. And that's all there is to do for number 4. I don't need to rewrite number 4 as repeated multiplication. Problem 6. There's a negative written in front of the Z, and that might make it tricky. So anytime there's a letter with just a negative sign next to it, that problem can be rewritten with a coefficient more obvious. This problem number 6 that was given, negative Z to the 8th, means negative 1Z to the 8th. Just a lot of times when a coefficient is a 1, we don't write it. But anytime there's a negative in front of a variable or a negative in front of a letter, it's an implied negative 1. And so I have to think of number 6 like this. Even though it's not written as negative 1Z to the 8th, that's what this means. And when I rewrite it like this, it probably makes it a little bit easier. So again, the exponent is usually what I attach first because it's the easiest. Not going to mess me up on any problem. The exponent is 8. Since there isn't a parentheses, the base is the letter directly attached, directly next to the exponent, which is the Z. And it would have been easy to mess up the coefficient in this problem because it wasn't written and it's supposed to be a negative 1. On number 8, so again, you should pause the video, hopefully have 1, 3, and 5 done. And again, maybe you can do 1, 3, 5, 7, 9, and 13 without watching more of me doing 1 through 14. If you can do all of 1 through 13 odds, then fast forward to me doing problem 16. If you get something wrong between 1 and 13 odds, then keep watching the video over this section. So problem 8 is the first problem where I don't see an exponent, and similar to number 6, when a number is assumed but not written, it's generally that number is assumed to be a 1, and that's the case in problem 8. So in problem 8, negative 5y is the same as negative 5y to the first power. If no exponent was written with a variable, the exponent's assumed to be 1. So I had to know that little fact that we use a lot. We usually generally don't write exponents that are 1. So in this problem, even though it wasn't written, I had to know the exponent was 1. Because there isn't a parentheses, the base is just the letter that's directly next to the exponent after I wrote the exponent in. And because there's not a parentheses, the coefficient is the number directly to the left of the letter. So it's going to be negative 5. So the next two problems have parentheses. And in parentheses problems, the base is the contents of the parentheses. So in problem 10, I see the exponent, so that's easy for me to identify. The exponent in problem 10 is the high number, which is the number 3. And when there is a parentheses, the base is the entire contents of the parentheses, which is 8y plus 1. When there is a parentheses, the coefficient is the number in front of the parentheses. In this case, I have a nice 15. And that's all there is to do for number 10. 12, I'm probably going to rewrite it because when I don't see a number and I just see a negative sign, I need to think of that negative sign as a negative 1. So when I go to do problem 12 and likely problem 11, if there's just a negative sign outside of parentheses, just like there's just a negative sign in front of a letter, that negative is an implied negative 1. So thinking of the problem like this, it's easier to do the questions. The exponent is the superscripted part, which is the 7. And when there's a parentheses next to when the exponent is outside of parentheses, the base is the entire contents of the parentheses, and when there's a parentheses, the coefficient is the number to the left of the parentheses, in this case is -1. Last one in this grouping of problems, there wasn't a number in front of the parentheses, and there wasn't a negative sign, so in problem 14, the number that's implied in front of the parentheses is a 1. So when I go to answer the questions for 14, the exponent is the number 7, it's the superscripted part. The base, when there's a parentheses, when there's an exponent outside of parentheses, the base is the inside of the parentheses, and when there's a parentheses, the coefficient is the number to the left of the parentheses. If there's no number written, it's an implied one. That's everything that needed to be done for the problems in 1 through 14. You should understand, like a problem like 15, it means 15 times 8y plus 1 times 8y plus 1 times 8y plus 1, because any integer exponent is shorthand for repeated multiplication. Should always understand what the repeated multiplication is. An exponent of 3 in problem 10 told me to multiply the base 8y plus 1 3 times. I don't multiply the coefficient 3 times. You only get one coefficient and 3 bases when I have an exponent of 3. So that's everything in the first 14 problems. Now I'll move on to the next group of problems. And the next group of problems start to introduce rules of exponents. And we're going to have 3 rules of exponents. And those rules I usually do with words and with symbols. And this first page is going to help me through one of the 3 rules. And I'll say the rule 1 of exponent, I'll call the multiply to add rule. Sometimes, or sometimes I might call it the product to addition rule. Product means multiply, addition means add. I'll do how about product to sum rule, because that's product. Product is add, sum. Product is multiply, sum is add. And the rule says this. This is the formal definition of the rule. It says if I have this problem, x to the m power times x to the n power, this equals x to the m plus n power. That looks more intimidating than it is. For problem 16, doesn't have x's, it doesn't have m and n's, but this is a multiply to add rule. The rule says if you're multiplying and the terms have the same base, so I'll say when multiplying, I'll say factors are terms. When multiplying, I'll say factors. I don't know that that's as good as terms. Oh, terms, I'm debating. So the rule in English says if you're multiplying terms with the same base, you don't change the base, you just add the exponents. So this is the rule above it, the multiply to add rule, which is the same as the product to sum rule or the product to addition rule, says if I'm multiplying terms with the same base, in this case the bases were x, you don't change the base, you add the exponents. Problems 16 and 18 are perfect applications of the multiply to add rule, because in problem 16 I'm multiplying 2 terms. The first term is y squared, its base is y. The second term is y to the 5th. Its base is y. When you're multiplying terms with the same base, so first term has a base of y, second term has a base of y, you don't change the base, you just add the exponents. So the answer to problem 16 is just going to be y to the 7th. I'm done with the problem because I've used the rule. I'm multiplying two terms with the same base, so I added the exponents. I can show you why it works. It's not horribly important, but it's nice to know, why does the rule work? Or I'll show you how can I do it otherwise. So anytime I have an integer exponent, I can change that to repeated multiplication. So I could have, if I didn't know the rule, rewrote the y squared as y times y. I didn't really need the times sign here, but I wrote it anyways. And I could have write y to the fifth as 5y's being multiplied. If I wrote the y squared without the exponent and the y to the fifth without the exponent, then I'd get this. I'd get a string of 1, 2, 3, 4, 5, 6, 7 y's being multiplied, and a string of 7 y's being multiplied with or without a times sign. When you write letters next to each other, the times sign isn't necessary. The times sign is implied when the letters are written next to each other. That's still that's 7 y's being multiplied, which is y to the 7th. So this is just a shortcut to keep me from having to write this is 2 y's, this is 5 y's, get a string of 7 y's being multiplied, which is y to the 7th. Problem 18, I'm multiplying two terms, x to the 5th and x. Those terms have the same base, and if you're multiplying terms with exactly the same base, you don't change the base, you just add the exponents. So if I was doing problem 18, I want to use the rule. First one, the base is x, the exponent is 5. The second x, the base is x, and when there's not an exponent written, the exponent is 1. So I'm multiplying terms with the same base. To do the multiplying, I don't change the base, I just add the exponents. And the answer to problem 18 would be x to the 6th power. Again, I could do this, why does this work? The x to the 5th is 1, 2, 3, 4, 5 is being multiplied, and then times the regular x. That gives me a string of 6 x's being multiplied, 5 from the first, 1 from the second, and a string of 6 x's being multiplied is what x to the 6th is shorthand for. In problem 20 and 22, multiplication's commutative, so I can, if I'm not comfortable with the rules of exponents, I can group the coefficients and the bases separately. So I can rewrite this because multiplication's commutative. You can change the order of any multiplication without changing the answer. I'm going to switch these just so you can see maybe why I do what I do for an answer. So I'm going to write 5, and I can't write 53. I'm going to write 5 times 3, and then y times y squared. This is equal to each other because in the original problem there's 5 times y times 3 times y squared. This is 5 times 3 times y squared. Changing the order in the multiplication problem doesn't change the final product. It just might make it easier to do the product. And in problem 20, I'm going to multiply the 5 and the 3 just by not using any rules of exponents. I'm going to multiply the 5 and the 3 by just multiplying those. And I know that 5 times 3 is 15. And for the y's, I'm using the rule, I'm multiplying two y's, they have the same base. When I multiply the y's, I add their exponents because I have a y times y squared. That's really 3 y's being multiplied, so it's going to be y cubed. But I'm not going to do that. Expansion, I'm just going to add the exponents. The first y has an exponent of 1 that's implied, and I'll get 15y cubed for my answer. For 22, the parentheses signify multiplication, so this really is negative 4z cubed times 2z squared. And if I need to, I can rewrite the order so that the terms that need to be multiplied together are more obvious. So I can think of this as negative 4 times 2 times z cubed times z squared. And letters next to each other with or without a times sign means times. And now I'm going to multiply the number parts together. Negative 4 times positive 2 is negative 8. Z cubed times z squared is z to the 5th. So hopefully you have at least paused the video and tried like some of the even problems like 15, 17, 19, and 21. And if you feel good about what I've done, maybe you're going further and trying 23, 25, until we get to the next group of problems. 24, I'm going to reorganize by just switching these. Because multiplication is commutative, you can switch the order of any multiplication problem without changing the product. You get the same result. And when I'm rewriting this, you don't need to write time signs between variables. The times is implied, so I just wrote the problem to be equal to the problem above it. So I should probably write an equal sign saying the problem that I just wrote and the problem directly above it are equal to each other. If you don't write the equal sign, I'd never take points up, but it's nice to write so I know that this is equal to something else. And now I'm going to get from 2y's down to 1y. Here the y's are being multiplied, and when you multiply when you have the same base, you add the exponents. And similarly with the z's, there's two z's being multiplied, the bases are the same, I add the exponents. When the exponents weren't written, there were an exponent of 1 that's implied that I kind of shoved in. And so I get y to the 5th, z to the 4th. 26, I can leave the problem in the order that it's in and get the right answer. I can shuffle the orders around. I can group the x's next to each other. I can group the y's next to each other. And I can group the z's next to each other. And that's completely legal to do. I can shuffle the order, and when there's 6 things being multiplied, I can make it in any order that I want. That's going to equal to the line above it. And when I rewrite it like this, it makes it easier for me to understand what needs to be combined and how to combine it. So now I'm just going to use the product to sum rule, make the 2x's to 1x by adding their exponents. I'm going to make the 2y's down to 1y by adding their exponents. Each of the y's has an implied exponent of 1. And I'm going to make the 2z's down to 1z by adding their exponents. So the best answer I could get here is x to the 5th, y to the 2nd power, and z to the 7th. 28, I don't need the parentheses. If the problem was written 6xy times 2y cubed, would have the same meaning as the original problem. Generally, I don't rewrite. I'm experienced enough that I know what to multiply without rewriting, but I could write this as 6 times 2 times this x times that y cubed. And when I rewrite it like that, if you didn't know what needed to be multiplied, maybe that should inspire you. So I'm going to multiply the 6 times 2 and get a 12. I'm going to leave the x in my answer, but the exponent on the x doesn't need to change because there wasn't another x to multiply it by. And I'm going to multiply the y's by using the product to sum rule and add the exponents and get a y to the 4th. 32, if I was to rewrite it without the parentheses, I'd say it's 4rs squared times r cubed s. And again, I can shuffle the order around. I can go 4r, r cubed, s squared s. The 4 is going to be part of my answer, but there's nothing to multiply it by. So when I go to write my answer, I'm going to have the number 4 first. Usually you write the coefficient first. And for the r's, the first r has an exponent of 1 that's implied but not written. The second one has an exponent of 3, so I add the exponent on the r's. For the s's, the second exponent on the s was a 1. I add the exponents and get an s cubed. Hopefully I haven't made a mistake. I don't feel like I have, but if I've made a mistake, just let me know, shoot me an email, or come visit me in my office, and I will, tell everybody that I messed up. So 33 through 52 has my next rule, and it's I'll say it's the divide to subtract rule. We could also call it the quotient. Quotient is another word that means divide. To, difference is another word that means subtract. And the quotient to difference rule, if I wrote it with x's, it would say x to the m power divided by x to the n power is x to the m minus n power. And in words, it says when dividing terms with the same base, subtract the exponents. Don't change the base. So problems 34 and 36 are perfect examples of this rule, because in problem 34 the x's are like the a's and the exponents, the m and the n are the 5 and the 3. The rule says for problem 34 that a to the 5th over a cubed is a to the 5 minus 3 power, and my answer to problem 34 is going to be a squared. And just like I did at the beginning of the last grouping of problems, I can show you, how could I do this problem if I didn't know the rule? So I can do this another way to solve. And the other way is to write the problem without the exponents. A to the 5th over a cubed can be written as 5a's being multiplied in the numerator and 3a's being multiplied in the denominator. And I can cancel 1, 2, 3 of the a's from the numerator with all 3a's in the denominator. And when I do that canceling, in the numerator I have 2a's. In the denominator I've canceled everything, so I leave a 1 behind. And any fraction that has a 1 in the denominator, you don't need to write the denominator, and the 2a's in the numerator are equal to a squared. So that would be how I would get the answer to a to the 5th over a cubed if I didn't know the difference to quotient rule. In 36, I'd have to think of this problem as b to the 7 over b to the 1st. I'm dividing terms with the same base. The bases are b. So when I divide terms with the same base, I subtract the exponents, and I don't change the bases. So the answer to problem 36 is just going to be b to the 6. And again, an alternate way to solve, if I wanted to solve it without the rule, I'd say this is 1, 2, 3, 4, 5, 6, 7 b's over 1b. And when you have 7b over 1b, you can cancel the 1b from the denominator with one of the 7b's from the numerator. I've canceled the entire denominator of the fraction, so I don't need to write a fraction anymore. And what I have left in the numerator is 6b's being multiplied, and 6b's being multiplied can be written as b to the 6th power. So the rules, the shortcut rules that we're learning, they can be avoided, but it's better to do them with the rules because it's easier. Problem 38 is 2 to the 6 over 2 squared. This is the first one my calculator can do. Let me just do this on my calculator just to get you used to using this calculator. So my calculator does exponents and fractions really exceedingly well. To do a fraction on my calculator, if I wanted to do 2 to the 6 over 2 squared, the first thing I'm going to do is hit the fraction button. The fraction button is kind of above the 7, below the calc, below the shift. If I hit the fraction button, my calculator gives me a fraction. Now I'm going to type the number 2 from 2 to the 6th. And then to get an exponent on this calculator, the x with a little square in it is what you need to hit. So I'm going to hit the x with a little square in it, and it gives me a square with a flashing cursor. I want to type the number 6 into that square. And now I have the numerator. I need to get down and enter something into the denominator, so I need to get down into this box. You do this by just pressing down with your replay button up here. I just hit down. Now my cursor is flashing there. I'm going to type the number 2, and then the x in the square key with the exponent, and then squared. And this calculator will tell me exactly what this equals to. Specifically, my answer should be 16. Generally, when we have a number, we don't write the number with an exponent, and 16 is a better answer than 2 to some power. If I was doing this using the rules, so without my calculator, I'm dividing two terms, 2 to the 6 and 2 squared. I'm going to use the divide to subtract rule. And I'll get an answer that's correct, but looks different than my calculator's answer. So the divide to subtract rule says 2 to the 6 over 2 squared is 2 to the 6 minus 2 power, which is going to be 2 to the 4th power. And 2 to the 4th power is 2 times 2 times 2 times 2, which is 16. If I did 2x with a square and type in 4, I can get my calculator to tell me that this is 16 as well. I think I just can't see it all the time. Generally, when a number has an exponent, we usually figure out what that number equals without the exponent. It's better. And so you'll rarely see me write an answer with a number with an exponent. You'll often see me convert that to the integer that it's equal to. 40 I could do in my calculator again, so I should just get used to my calculator. So for 40, I'll go fraction, hitting the fraction button, and then 3, and then the x with the square button, 4, down with my replay button, 3, the x with the open square button, then 3, and then hit the equal sign in the bottom right hand corner, and I think that's readable. The answer to problem 40 should just be the number 3. And to get this without a calculator, I'm going to use the divide to subtract rule. This would be 3 to the 4 minus 3 power, which is 3 to the 1st power. And anything to the 1st power is itself. We almost never write an exponent of 1. And it'd be better just to write the number 3, but 3 to the 1st power and 3 are equal to each other. 42, I need to treat the a's separately from the b's. So I'm going to make the two a's into one a by subtracting their exponents. And I'm going to make the two b's into one b by subtracting their exponents. And again, I probably wouldn't show as much detail as I'm showing if this was your homework question and all you did is wrote the answer a cubed, b cubed. I'd be completely content with that because it certainly isn't necessary to show that step if you could do that step in your head. Problem 44, the b in the denominator has an implied exponent of 1. I'm going to do 44 just like I did 42. For the a's, I'm going to go a to the 4 minus 2 power. For the b's, I'm going to go b to the 2 minus 1 power, which is going to give me a to the 2nd, b to the 1st. That's probably not what I'd write for my answer because I generally don't write an exponent when it's 1. It's because the 1 is implied. Probably a better answer for 44 would be a squared b. In 46, I'm going to treat the numbers just like kind of like I did in the multiplication problem. I'm just going to divide the numbers. So in 46, I'm going to divide the 10 and 5, and I'm going to subtract the exponents on the x's. I've kind of separated the numbers from the letters, not for any special reason, just so you can kind of know that they're separated from each other. And for my answer, 10 over 5 is 2. For the x's, I subtract their exponents. And for my answer, I'm going to get a 2x squared. 48, I'm going to treat as kind of 3 problems. I'm going to simplify the fraction 16 over 6. The a is not going to change. It's going to stay in the numerator of my answer. And I'm going to simplify the b's by subtracting their exponents. So 16 over 6, pretend I didn't know how to reduce 16 over 6. Could break this calculator out, enter the fraction 16 over 6, hit my fraction button, do 16 over 6, then hit equals, and my calculator will tell me that it reduces to 8/3. So my calculator, if I'm not good at doing fractions, does amazing things with fractions. I knew how to reduce this. Because to reduce 16 over 6, I go 16 divided by 2 is 8. 6 divided by 2 is 3. So part of my answer is going to have an 8 in the numerator and a 3 in the denominator for the reducing 16 over 6. The a started in the numerator, didn't have anything to combine it with, it's going to stay in the numerator. The b's, I'm going to subtract their exponents and get a b squared. So 8ab squared over 3 is the best I can do for an answer to 48. 50 and 52, the base for 50 is 3x. And when we're simplifying terms, dividing terms that have the same base, we don't change the base, we subtract the exponents. So in this problem, the base is 3x, and when you're dividing terms with the same base, you leave the base unchanged and you subtract the exponents. So when the base is in a parentheses, when I do the rule for dividing with the same base, I'm going to use that rule, and I'm going to subtract the exponents and leave the base unchanged. So my answer to this is going to be 3x quantity cubed. In the next group of problems, we'll learn how to simplify this, but if you were working ahead of me and you wrote something down a little bit different, there's a better answer to this, and it's kind of premature, but it would be okay and probably better if you're asked to cube a parentheses that doesn't have any addition in it, then you can just cube each of the numbers and letters in the parentheses. And so 3x quantity cubed means 3 cubed times x cubed. My calculator can do 3 cubed for me if I don't know it. So 3 exponent 3 is 27. So it'd be too early for most students right now to write this as an answer. That involves knowing the last rule of exponents that I haven't talked about yet, but I will pretty quickly here. But if you wrote that for an answer, that's probably by the time we get through with this section, by the time we get to the test, the answer that I would expect. I'm going to do 52 just like 50. The base in 52 is x, y, z. Both terms have the same base. And when I'm dividing terms with the same base, I subtract the exponents. And when I subtract the exponents, here I get x, y, z to the 4th. And that's completely great for an answer at this point because we don't have the rule that tells us how to reduce a parentheses. But it would be better if a parentheses doesn't have any adding or subtracting. You can simply raise everything inside the parentheses to the power outside the parentheses to write it without the parentheses. So the quantity x, y, z all to the 4th, or x to the 4th, y to the 4th, z to the 4th, they're all good. 53 through 76 has the last rule, and I'd call it the, oh gosh, how about the power to product rule? And I kind of, in shorthand, well, the rule is this: x to the m to the n power equals x to the m times n power. And it basically says if a single base has 2 exponents that apply to it, to the single base, we simplify by multiplying the exponents. So that's the 53 through 76 will all be variations of this rule. There might be more than one base, but every base is going to have multiple exponents that apply to it. And so 54 and 56 are the simplest version of this rule. In 54, the y is kind of like the x, and the 2 and the 3 are the m and the n. And to do this, I have one base y. It has two exponents that apply to it, 2 times 3. And to do these simplifications, you multiply the exponents. The answer to 54 is supposed to be y to the 6th. And again, if I didn't know the rule, I certainly could have gotten this without knowing the rule, but it's harder. So to simplify without knowing any rules, or without knowing many rules, I can rewrite the problem without the exponents. So let me do the cube first. Y squared cubed means y squared times y squared times y squared, because to cube something means you get 3 of those. And in this case, I'm cubing y squared, so I get 3 y squareds. I didn't put time signs between them, but that's implied. And then each of the y squared is 2 y's being multiplied. So I can change y squared times y squared times y squared. I can make each of the y squareds into 2 y's. This gives me a string of 6 y's being multiplied, and a string of 6 y's being multiplied is equal to y to the 6th. So each of the problems that I'm using a rule to solve, if I'm patient and really know my algebra rewriting well enough, I can probably solve them all without knowing any of the rules, but the rules just make it quicker. If I was doing problem 56, to simplify it without the rule would be ridiculous, because I'd have to wind up writing 20 x's. Here I have one base x, 2 exponents that apply to it. If there's one base with 2 exponents that apply to it, you generally simplify by multiplying the exponents. So my answer to 56 is going to be x to the 20th. And again, for probably if 54 or 56 made it onto the test, I would write the answer without showing any work. And that's okay on the test. If problems can be done without showing work, you can do them without showing work. The problem is that if you don't show any work and you get a wrong answer, I've got no room to give you partial credit. So if you did problem 56, let's say you wrote x to the 9th for an answer, if this was a test question, but you showed this middle step that you meant to multiply these, and then you didn't multiply them, you added them, I would give you partial credit if you showed the step, well, I knew I was supposed to multiply these, but I just multiplied them wrong. So if you just showed the answer and you wrote the wrong answer, like x to the 9th, if it was a 3-point problem, you'd get a -3. If you showed, oh, I knew to multiply, but I didn't multiply even though I knew to, then you get some sort of partial credit, maybe -1 or -2 as opposed to minus everything. In 58, the exponent a has 2 exponents that apply to it, 4 and 5. The exponent b has 2 exponents that apply to it, 3 and 5. And so I'm going to use the rule to say if I have a single base that has 2 exponents, I simplify by multiplying the exponents. Generally, you only ever use this rule when there's a parenthesis. If there's not a parenthesis, then it's very unlikely that you're going to have 2 exponents apply to one base. So in 58, my answer is going to be a to the 20th, b to the 15th. Again, I could do this without knowing the rules, but it would be ridiculous. And I could do it without showing any steps. In 60, I would probably just do it like this. I'd say this is x to the 3 times 4th and y to the 4th. If a letter doesn't have an exponent inside applying to it, I just attach the exponent from the parentheses to it. That's the nicer way to do it. And again, this rule, when you have multiple letters inside of parentheses, only works if there's straight multiplication in the parentheses. If this problem said x cubed plus y to the 4th, then you can't just multiply the exponents. We'll get to that in section P5. Section P5 was like the worst video of the semester. It's so long. But anyways, I'll try to tell you in that section when this rule may not work so well. And the rule doesn't work so well when there's a plus sign in or minus sign in the parentheses. If I wanted to do this problem differently, I could have thought of the y as having an exponent of 1, because that y certainly has an exponent of 1, and then I could say this is x to the 3 times 4, y to the 1 times 4, and I'll still get exactly the same answer of x to the 12th, y to the 4th. So when I have a single letter that doesn't have an exponent, I can certainly give it an exponent of 1, and then now I'll have two exponents that apply to a single base, and I can multiply the exponents, or I could just attach the exponent to the letter, and it's easier just to attach the exponent to the letter. And again, this rule that I'm using for 58 and 60 wouldn't have worked if the problem, like if 58 was a to the 4th minus b cubed to the 5th, then I couldn't, that's not going to equal to a to the 20th minus b to the 15th. It's way more complicated when there's an adding or subtracting inside a parenthesis. The rule that when I have multiple letters only works if the parentheses only has multiplication in it. 62, I could just do this. Make it 2 to the 5th power x to the 3 times 5 power. That's generally how I would do it. When there's a parenthesis that only has multiplication inside of it, everything in the parentheses needs to be raised to the 5th power. Numbers are letters without exponents. Usually I just attach that exponent to, and letters with exponents, I multiply the exponents. 2 to the 5th I can do on this calculator if I don't know it. So I'm going to go 2x with the square button for my exponent, and then 5. And that'll give me 32. And then I can do the x's by myself without my calculator. I could have, if I really wanted to, treated the 2 just like it was a letter. So another way to do this, which is not really the way that I generally would do this, I could have considered this 2 to the 1st, x to the 3rd to the 5th, and then I can go 2 to the 1 times 5, x to the 3 times 5. That will give me 2 to the 5th, x to the 15th, which is 32x to the 15th. And look at how I wrote a wrong answer there. That's x to the 15th. Hopefully this thing isn't littered with mistakes. I do silly things like that, and students always do that on the tests too. Students will know how to do a problem, they'll write everything down, and then somehow they just make a mistake. And because I make mistakes like that too, I try to definitely give you as much partial credit as I can. If you just make a silly mistake like that and forget to multiply the 3 and the 5, well then you're going to get credit for it, partial credit. You'll lose something because you made a mistake, but it won't be everything. 64, I'm going to go 3 cubed, x to the 2 times 3, y to the 4 times 3. I know that 3 cubed is 27, but I could go 3 exponent 3 to get my 27. Again, generally I won't write a number with an exponent, especially because it's not terribly hard to figure out what it's equal to generally. So a better answer, or the best answer for problem 64 would be 27 x to the 6th, y to the 12th. '66, I'm going to go 3 squared x squared y to the 2 times 2. 3 squared means 3 times 3, which is 9. The x is just going to stay in x squared, and the y I'm going to multiply the exponents. The rule that we've been using applies to fractions as well as multiplication problems. And as long as there's not an adding or subtracting, if there's just straight multiplication or straight dividing or a combination of multiplying and dividing inside of parentheses, I can use the rule to clear the parentheses. I'm going to make this x to the 4th. The y has the exponent of 3 and 4 that apply to it, so I'm going to multiply the exponents. And for my answer, I'm going to get x to the 4th over y to the 12th. Again, I could have considered this x to the 1st, y cubed to the 4th, and made it x to the 1 times 4, y to the 3 times 4. That's kind of a little overkill. I used to only do this, but then that kind of started to feel ridiculous. For 70, each of the letters has 2 exponents that apply to it. The z has an exponent of 7 and 3, the y has an exponent of 4 and 3, the x has an exponent of 1 and 3. So I'm going to multiply the exponents For the x, I'm just going to attach the 3. For the z, I'm going to go 7 times 3. For the y, I'm going to go 4 times 3. And for my answer, hopefully I'm not getting so tired that I'm getting everything wrong, I'm going to get x cubed, z to the 21st, y to the 12th. For 72, I'm going to go 5 cubed, which is 125, x cubed, which is just x cubed, y to the 3 times 3. Again, if you can't do 5 cubed in your head, you go 5 exponent 3, and you'll find out that it's 125. Generally, I don't leave numbers with exponents. I figure out what they equal to without their exponent for a better answer. So my answer is going to be 125 x cubed over y to the 9th. Got to be getting close to the end of this section. Sorry for the videos being long and beyond dull. Like last week I was out and about and I ran into a student, and it took my college algebra class watching my videos, and I don't know that this is even appropriate for a video, but he came up to me and he goes, I got to tell you a secret. He goes, every time I sat down to watch your video, I smoked marijuana first, and then I watched your video, and somehow it made it more tolerable. And I really don't want that to be the case. I don't need anybody doing any drugs to get through my lectures, but that's what he said he needed to do. So I felt horrible, but they're long, they're dry, and hopefully you're using the fast forward button on them when you know how to do something. But I don't want to undersell the students that need everything, so I try never to skip steps. I try to show everything I can possibly show, and if you need less, just fast forward to it. But if you need more, rewind it, and if my videos aren't enough, you can always call me or visit me, and you won't have to resort to any illegal substances to get through this. So let me finish these up here. So 74, I'm going to say this is 2 to the 4th, z to the 7th times 4, 3 to the 4th, y to the 4 times 4. I know 2 to the 4th, but 2 up arrow 4 if you don't is 16. Yeah, I sensed that student probably was going to smoke marijuana regardless of my videos, so maybe it's just saying that to be cool, I guess. Who knows? The 3 to the 4th is 81, and the y to the 4 times 4 is y to the 16. So the best answer for 74 is 16, z to the 28th, 81, y to the 16th. 76, I'm going to go 3 to the 4th, x to the 4th, 4 to the 4th, y to the 2 times 4. Again, if there was a plus or minus anywhere in this parentheses, I couldn't do this. 3 to the 4th I just did, that's 81. 4 to the 4th I think is 256. But I'm going to check that out real quickly to make sure I'm not just saying something that's stupid. So 4 up arrow 4, and I get 256. And for the y, I get y to the 8th. Getting there. Just a few more problems. Parentheses, multiple ugly problems. So to do problem 78, I have to deal with the parentheses that has an exponent outside of it first. So first I'm going to do that parentheses and get it to be a to the 2 times 2, b to the 3 times 2, and I'm going to leave the second parentheses as ab to the 4th. This is going to make the first parentheses turn into a to the 4th, b to the 6th. The second parentheses is still ab to the 4th. You don't have to, but I'm going to rewrite this without the parentheses with the letters next to each other. I'm going to rewrite it as a to the 4th, a, b to the 6th, b to the 4th. This is going to use now the new rule. To clear the first parentheses, I use the one letter multiple exponents, multiply the exponents. Now I have 2 letters being multiplied, so I add their exponents. So the best answer I could come up with for problem 78 would be a to the 5th, b to the 10th. I'm going to attack problem 80 the same way. I'm going to get rid of this parentheses. I'm going to get that exponent of 3 dealt with first. by going 5 cubed, a to the 2 times 3, b cubed. The second parentheses doesn't have an exponent in front of it, so I'm going to leave it alone for a second. 5 cubed I can do on my calculator if I didn't know it was 125. And then the a is going to become a 6 for its exponent. So I got the parentheses away from the exponent away from the first parentheses. Now I'm going to rewrite it without the parentheses in a nice order, writing the numbers next to each other, the a's next to each other, and the b's next to each other. The second a that I wrote needed an exponent of 1. I'm going to multiply 125 times 3, which is 375, and write that in my answer. And I'm going to add the exponents on the a's and add the exponents on the b's. So it's kind of a blended problem that uses 2 rules. First rule, I had to multiply exponents because each of the bases had 2 exponents that apply to them. The second rule, when you're multiplying, when you have 2 bases and 2 exponents, you add the exponents as opposed to multiplying. Last 3 problems. 82, I'm going to make the first parentheses into 4 squared, x squared, y to the 4 times 2, which is y to the 8th. And the second parentheses into 2 cubed, x cubed. I'm going to do double step here, which I normally don't do, but I'm going to do 4 squared is 16, 2 cubed is 8. I'm going to get rid of the exponents and write things in a nice order, which means grouping the x's, leaving the y kind of tagging along. I think that's 144. I don't know that. 16 times 8, 128. I thought wrong. So in my answer, the number 16 times 8 multiplied to be 128. When I rewrite the x's next to each other, they're being multiplied, so I add their exponents, and the single y just is going to be part of the answer. Problem 84, neither parentheses has an exponent, so I can just rewrite it in a nice order. Go 3 times 4 times x times y cubed times y, tack on an exponent of 1. I wrote time signs, but I certainly didn't need time signs between the letters. And now for my answer, it's going to be 12x y to the 4th. Last problem. First parentheses I'm going to leave alone at 3a squared b. Second parentheses I'm going to make 4 cubed b cubed. Now I'm going to write it in a nice order, and the 4 cubed is equal to 64. So I'm going to go 3 times 64 times a squared from the first parentheses and b from the first parentheses, and then times b cubed from the last parentheses. I think 3 times 64 is 192. Which it is. You're allowed to use calculators on the test, so you might as well get used to whatever calculator you're going to use. I really want you to use this one because it's going to be the easiest and best calculator for this class. So I get 192, and then an a squared, and for the b's, you have a 1 and a 3 for the exponents, so you get a b to the 4th. So hopefully you're done watching this video and you've done every odd problem in the section. That's always my hope, that by the time you get done watching a video that you're done with all the odd problems and you can just move on to the next section. I'll stop here because I can't imagine anybody else is listening. So thanks for making it this far.